Hello student, I am going to start from the last video, that is we are discussing about JPEG image conversion technique. So we have concluded the last video in this equation, that is discrete cosine transform, which is used to convert the information of the pixel or the image information to the in the frequency domain using the discrete cosine transform functions. So here the explanation of this function is that we begin examining this formula by realizing that only constants come before the brackets. So here you can see in this equation that we have discussed in the last video also, start with that one. So here two constant Cu and Cv are the only constant used in these equations. That is, we begin examining this formula by realizing that only constants come before the brackets. Next, we realize that only 16 different cosine terms will be needed for each pair of UV. So there will be 16 pair of 16 different cosine terms will be needed for each different pair of UV values. So we may compute this ahead of time and then multiply the correct pairs of cosine terms with a spatial domain value for that pixel. So so that is why we need 16 pairs of this type of value. So before doing the conversion, we can already create that 16 or we can already calculate the 16 different cosine terms which will be multiplied with the spatial value, or we can say the information value contained in the pixel directly. So that is what it is saying, that we realize that only 16 different cosine terms will be needed for each different pair of UV values. So we may compute this ahead of time, means we can compute these 16 different cosine terms ahead of time and then multiply the correct pair of cosine terms to the spatial domain value for that pixel. So there will be 64 addition in two summations. So there will be 64 addition in two summation, one per pixel. Finally, we multiply the sum. So there will be 64 additions in two summations, one per pixel. And finally, we multiply the sum by the three constants to get the final value in the frequency matrix. This continues for all UV pairs in the frequency matrix. Since U and V may be any value from 0 and 7, the frequency domain matrix is just as large as the spatial domain matrix. So size remains same. The frequency domain matrix contains the value between minus 10242 plus 1023. The upper left entry also known as the DC value or discrete cosine value, and the average of the entire block. So upper left entry also known as discrete cosine value in the frequency domain matrix is the average of the entire block and is the lowest frequency cosine coefficient. As you move right, the coefficients presents cosine functions in vertical direction that increase in frequency. Likewise, as you move down, the coefficients belong to increase using frequency cosine functions in the horizontal direction. So diagonally you can say it is increasing the value. The highest frequency values occur the lower right part of the matrix. The higher frequency values also have a natural tendency to be significantly smaller than the low frequency coefficients since they contribute much less to image. So try to understand this line. The higher frequency values also have a natural tendency to be significantly smaller than the lower frequency coefficients since they contribute much less to the image. So higher frequencies does not give or higher does not give any importance or contributions in the image. So typically the entire lower right half of the matrix is factored out after quantization. So typically the entire lower right half of the matrix factored out after the quantization, because that does not contribute that much in the image. This essentially removes half of the data per block. So due to this removing of the information or the frequency domain values or the frequency matrix, half frequency matrix values, because those does not add anything or contribute anything in case of the image, because those have high frequency, so we are losing or we are removing half of the data. So this essentially removes half of the data per block, and we have 64 blocks. Oh no, sorry, not only 64 blocks, 64 pixel block. So there might be lots of blocks having 8 by 8 blocks, 8 by 8 pixel in each block, which is one reason why JPEG is so efficient at compression. So computing the DCT is the most time consuming part. So that is why, but this part, only this computation of DCT is the most time consuming part of JPG compression. That determines the worst case running time of the algorithm. So the worst case running time of JPEG algorithm depends on the computation of DCT. The running time of algorithm is discussed in detail later. However, there are many different implementations of the discrete cosine transform. So obviously, however you are going to establish or evaluate these discrete cosine terms, in that way only you can achieve or enhance the performance or algorithm complexity. So if you execute the algorithm in different format of DCT conversion or DCT algorithm, then the complexity or time requirement will be different. So directly depends upon this DCT value computation. JPG compression complexity or time requirement in JPG compression is directly dependent on the computation of the DCT values. Finding the most efficient one for programmers situation is the main key. So there are implementations that can replace all multiplication with shift instructions and additions. Doing so can give dramatic speed ups. However, it often approximates values and thus leads to lower quality of output image. That also a very important matter to be understand, that you might change something or you might add something. Like here one example is that you might use some, like you might sense these multiplications with shift instructions and additions in case of the algorithm, which might reduce the time and increase the speed up, but in that way you will lose some information because you are going to take the approximate values only, and in that way you will lose lots of information, and thus it will lead to a lower quality of output image. So that is also a important matter to be concerned about. There are also debates on how accurately DCT algorithms compute the cosine coefficient and whether or not the resulting values have adequate precision for their situation. So any programmer should use caution when choosing an algorithm for computing an DCT and should be aware of every trade-off that the algorithm has. Third phase is the quantization. So first phase was the division, second phase was the conversion, then third phase is the quantization. So in the quantization, having the data in frequency domain allows the algorithm to discard the least significant parts of the image. The JPEG algorithm does this by dividing each cosine coefficient in the data matrix by some predetermined constant and then rounding up or down to the closest integer value. The constant values that are used in division may be arbitrary, although research has determined some very good typical values. However, since the algorithm may use any values it wishes, and since this is the step that introduces the most loss in the image, because due to the quantization only you will lose lots of information. Though in case of DCT you are reducing half of the block size data due to not importance of that frequency domain or high frequency values which does not give any contribute any in the image. So you are deleting some part or half part in case in the DCT phase, or you can say conversion phase. But also in quantization we are losing more than more data than the conversion phase, because we are quantizing it. As we know, in case we have gone through one video about quantization where we have discussed how we lost the data, because we are trying to approximate the values to the integer value. So in that way we are losing informations. So here also it is saying that JPEG algorithm does this by dividing its cosine coefficient, that the frequency domain value of the image in a data matrix by some predetermined constant, and then rounding up or down to the closest integer value. The constant values that are used in the division may be arbitrary, although research has determined some very good typical values. However, since the algorithm may use any values it wishes, and since this is the step that introduces the most loss in the image, it is a good place to allow users to specify their desires for quality versus size. Obviously, dividing by a high constant values can introduce more error in the rounding process, but high constant values have another effect. As the constants gets larger, the result of the division approaches zero. This is especially true for the high frequency coefficients, since they tend to be smallest values in the matrix. Thus, many of the frequency values become zero. So that is also one very interesting phase, because if you divide by a high constant value, it can introduce more error, and because you might find lots of information that will be rounded up to a near constant. But high constant values have another effect. But in the other hand, the constant gets larger, the result of the division approaches zero. So if your that constant value is higher, then division approaches near to zero. This is especially true for the high frequency coefficients, since they tend to be smallest values, because we are trying to take the high frequency coefficient values, since they tend to be smallest values in this matrix. Thus, many of the frequency values become zero. So in that way we might create some good algorithm also. Phase 4 take advantage of this fact to further compress the data. So this fact is take as advantage in case of phase 4, due to this fact of frequency values becoming zero if you multiply or divide by higher constant values. The algorithm uses the specified final image quality level to determine the constant values that are used to divide the frequencies. A constant of the 1 signifies no loss. On the other hand, a constant of 255 is the maximum amount of loss for a coefficient. So try to understand this part. A constant of 1 signifies no loss, because if you lose information about 1 having a value 1, if you lose that much of information, it will not create any difference. But if you lose a value about 255, obviously it will lose lots of information. So is the maximum amount of loss for that coefficient. The constants are calculated according to the user's wishes and the heuristic values that are known to the result in the base quality final images. The constants are then entered into another 8x8 matrix called the quantization matrix. Each entry in the quantization matrix corresponds to exactly one entry in the frequency matrix. Simply coordinates determine the correspondence. The entry at 35 in a quantization matrix corresponds to entry in the 35 in the frequency matrix. A typical quantization matrix will be symmetrical about the diagonal and will have the lower values in the upper left and higher values in the lower right. Since any arbitrary values could be used during quantizations, the entire quantization matrix is stored in the final JPG file so that the decomposition routine will know the values that are used to divide its coefficient. So this is one type of simple quantization matrix. So this is just the arbitrary numbers of constants that will be used to multiply with the frequency matrix. The equation used to calculate the quantized frequency matrix is fairly simple. The algorithm takes a value from frequency matrix f and divides it by its corresponding value in the quantized matrix q. This gives the final value for the location in the quantized frequency matrix f quantized. Figure 6 shows the quantization equation that is used for each block in the image. Here you can see f of uv means frequency matrix, q of uv means that is this is the matrix, and that is divided by this plus 0.5. By adding 0.5 to each value, we essentially round it off automatically when we truncate it without performing any comparisons. Of course, any means of rounding will work, so you can give any value also, but here you can see before quantization the frequency values are like this, and after quantization this will become like this, but it will reconstruct it like that. So this is before quantization. If you multiply this divide by this thing with these values, then you will get this one. Okay, then if you after reconstruction you will get this one. So this is the process of quantization. So quantization is nothing but we are trying to get a near integer value of the frequency value. So after quantization, the algorithm is left with blocks of 64 values, and many of which are 0. Of course, the best way to compress this type of data would be to collect all 0 values together. That is why this all 0 values has been collected together, and that belongs to the process of quantization. After quantization, the algorithm is left with block of 64 values, many of which are 0, because that is what it is saying in case of in this statement. Does many of frequency values become 0, because we are dividing high constant value by a high constant value, and which leads to lots of zeros and 0 entries in case of quantization matrix, and that is reconstructed by like this, and in case of phase 4 it is helping. Of course, the best way to compress this type of data would be collect all the 0 values together, which is exactly what JPEG does. The algorithm uses zigzag ordered encoding, which collects the high frequency quantized value into long string of zeros to perform a zigzag encoding on a block. The algorithm starts at a DC value and beginning winding its way down the matrix as shown in figure 7. This converts an 8 by 8 table into 1 by 64 factor. So here you can see this is a zigzag pattern uses to find that encoding technique. It goes like this to create a 1 by 64 factor from an 8 by 8 table. But here what happened is that they try to collect the zeros in one part of the matrix. So all of the values each blocks are encoded in a zigzag order except for a DC value, discrete cosine value. For all other values, there are two tokens that are used to represent the values in the final file. The first token is a combination of size and skip values. The size value is the number of bits needed to represent the second token, while the skip value is the number of zeros that precede this token. So it is thus here you can see size value is the number of bits needed to represent a second token. Means second token is skip. First token is combination of size and skip value. The size value is the number of bits needed to represent the second token, while the skip value is the number of zeros that precede this token. So the second token is simply the quantized frequency value with no special encoding. At the end of each block, the algorithm places an n block sentinel so that the decoder can tell whether one block ends and next beginning. The first token with size skip information is encoded using Huffman coding. Huffman coding scans the data being written and assigns fewer bits to frequently occurring data and more bits to infrequently occurring data. Thus, if a certain values of size and skip happen often, they may be represented with only a couple of bits each. So there will then be lookup table that converts the two bits to their entire value. So JPEG allows the algorithm to use standard Huffman table and also allows for custom tables by providing a field in the file that will hold the Huffman table. So actually point is that it is a very rigorous and lengthy process to convert an image into JPEG encoding technique. So please try to go through this content again. I am trying to conclude the things here. It's just I'm trying to provide the basic description of this JPEG algorithm and try to give some hint and information regarding this process. Try to go through the examples given here in this content or in this document, and it will be very helpful to understand. And also, if you find any difficulty, please let me know. I'll try to resolve that over Google Meet. So that's it. Thank you.